Okay, now after having seen how corpora look like in NLTK and what kind of properties corpora have, we want to do some statistical analysis on top of corpora. And to do so, we will first look into conditional frequency distributions because they allow us to compare data in our corpora along different dimensions, let's say along different classes. So what we have for a conditional frequency distribution, we should have a corpus split along different dimensions, such as different categories, or as we also call them, different classes. So the idea of a conditional frequency distribution is we first generate a frequency distribution in NLTK that's also called FreqDist. And this frequency distribution indicates how often an event could be a word, for example, occurs in a corpus, but conditioned upon a certain category. And then we want to see how the categories differ in their probability distributions or in their distributions across events. So in NLTK, there's something which is called conditional frequency distribution. That's what we're gonna introduce now. And we start out with some small illustration of where we want to be heading to. Let's say that our conditions are different genres, such as news versus romance, right? So this is news text, this is romance text, where romance is that's dealing with novels, right? So it's fictional literature versus news. This is newspaper. And we can let's go over some joint vocabulary, such as the, queued, Monday, and will, which are given in both of these text genres. But we can check the frequencies of the words along those two text genres. And what we would see, for example, here is that something like queued occurs very rarely in news, whereas it does occur much more frequently in romance. And on the other hand, a word like Monday does not occur very often in romance, but it would occur much more often in newspaper text. So how are we going to do this in NLTK? What we would do is, first of all, we consider unconditional FreqDist. So this is a frequency distance that just counts how often certain events occur in our, because we're in our context, because we're in natural language processing, our events could, for example, be words. So how often do words appear in a text? So it's just a frequency with which they appear in a text. And a conditional frequency dist is how often do they occur conditional on some event. And to achieve this in NLTK, we would first create pairs of conditions and events. Okay, so we do this by illustration here. Let's say you have a text like the Fulton County Grant, etc., etc., and then you generate first those pairs here, where in the first element of each tuple, you indicate which category this text is from. So let's say this text above here is from the news corpus, so we would feed in news here, right? And in our concrete case of the brown corpus, we would have 15 conditions because the corpus is labeled across 15 different genres, and we would have 1.2 million events corresponding to 1.2 million words occurring in the corpus. So we would create our pairs here, right? We had said we need to create those pairs. So how we would do this? We generate a list which contains a tuple, where each tuple is a pair of the condition and the event. And we go over the genres. Let's say we want to restrict ourselves to two genres, which are news and romance. And then we go over all the words in this genre, right? So check here that this is really the same genre here. So we go over the words in this genre, and this where the genre is news or romance. Okay, so we generate our list of pairs, and then we can count how many pairs do we have. It's 170,000 roughly. Good. So now we have this variable genre word contains all the pairs genre word from the news and the Romance domain. We can check by looking at the beginning. At the beginning, we have the genre news. So it starts out with the Fulton, as we have seen, and we can then check the end. So we go the end. So these are the last two words in Python notation of this array or of this list. And you'll see in the end is the Romance genre. It ends with afraid not. So we're afraid not. Okay. So now that we have our list of pairs, we feed that list of pairs into the NLTK method ConditionalFreqDist. We feed that in, and we name the variable CFD, standing for conditional frequency distribution. Then we type in CFD on the Python prompt, and it tells us this is a object conditional frequency dist, and it has two conditions, namely we had said Romance and news, right? And we also can check for the conditions, which indeed are news and Romance. Then we can assess those probability or those distributions. So we go in, we check, we type like in a dictionary notation, we type in Romance for the conditional frequency distribution, and then we get the frequency distribution for Romance, which is like which is a distribution over all the tokens. And yeah, it's a distribution over all the tokens conditioned on us being in the Romance genre. And if we want to check out a particular word, such as could, which we don't see here up here, how often it occurs in the Romance genre, then it will tell us that it is 193 times. Okay, so now that we've understood the basic principle, now let's do some concrete application with the Universal Declaration of Human Rights, which is also a corpus, namely the corpus of the Universal Declaration of Human Rights. So this is a rather short text, I think, and it has been translated into many languages because the Declaration of Human Rights should apparently be universal, so it should apply to all humans. So we also need to make it available to many different humans across different languages. So now we want to apply it to this, our conditional frequency distribution to this text corpus. So we first import the corpus from NLTK. Then we have, let's say we want to differentiate two languages, namely English and German at first. Again, we make our list of pairs, and this time note here the first element is the condition and the second one is the event. Okay, so the condition are our languages. So we have two languages. And what are our events? Well, our events are, and now in this case, let's say we're not focusing on the words, but on the length of words. So we want to see how English and German differ in the length of words. And note here that we append Latin 1 to the language denominator. So this is just because the languages are apparently named like this in the corpus and has no other functionality otherwise. Okay, so now we want to try out, we want to check how English and German differ in the distribution of length of words. And let's do some operation on our conditional frequency distribution up here. Namely, we outline what is going on in this frequency distribution, and we use the tabulate method for this. And you will see here by way of illustration what it's doing. So we have the two languages. These are our conditions up here, English and German. And then we have 8 different events. So these are given here by the samples, range 8. So we have 8 different events. And what we are showing here is how many words are of length 0 in English and German. Well, there are 0 such events, right? Because apparently all the words in the languages, they have at least one character, right? Then we check how many words in English and German have one character, and you see it's 185 and 171 in German. Then we check how many words have two characters, and we see it's like 525 in English and 263 in German. Now we have to pay attention here. Is it really 525 and 263? No, it's actually not, because we have something here which says cumulative true. So it really adds the event. So it's adding 1 plus 2. So what this actually means here, this means less or equal than 2, and this means less or equal than 3. So we have so the number of words of length 2 in English is actually this number minus this number, right? Because cumulative means you just add it up, right? Everything until you add up all the events which are less than equal to the number. Okay, good. So it means in English, let's again make an illustration. In English, there are 1283 words which have length less than or equal to 6, and in German there are 1030 such words. Good. And now also there's one thing to keep in mind when you do such a comparison between two languages. And this one thing that you should very much keep in mind is the size of the corpora. Let's say this could be very much misleading if the corpora were of very different sizes. Let's say the English corpus is 100 times as big as the German corpus. Then, of course, the English, or let's say the German, so here the German numbers are all smaller. Let's say the German corpus were 100 times bigger than the English corpus. Then the numbers for German would, of course, also be a lot bigger, just by the sheer fact that there are many more events in the German corpus. So in this case, we would have to normalize by the total sum of all events. But we don't have to do this right here, because this Universal Declaration of Human Rights is really, these are comparable corpora. They are all more or less of the same size. So like if there are 5 pages in English, then it's also going to be 5 or 6 pages in German, because it's a translation of one and the same text. Okay, but anyway, we do some plotting. So what we see here on the x-axis is how many words are less than or equal to k. How many words have less than or equal to k characters in, let's say, English, German, and now we add a third language, namely Finnish. So how many words have less than or equal to 10 characters in German, English, and Finnish? And what you see here, so this is a really interesting plot. You see here, like, let's say, like 750 words have less or equal than, where's 10? 10 is here. Let's say 11. So 780 words have less than or equal than 11 characters in English. And in total, if we go to 21, it's 1800. So let's say in English, overall, there are like 1,800 words. And like this is then 780 is like 99% or something. So in English, 99% of our words have length 11 or less. Now in German, it's much less. Let's say this is 80%, right? And in Finnish, it's even less. So what does that mean now? It means that, and conversely, like in English, almost no words are longer than 11. In German, like 20% of words are longer than 11, and in Finnish, like 30% of the words are longer than 11, let's say. So this means on average, Finnish, German has longer words than English, which we find very intuitive because German has compounding, right? So you can make words arbitrarily long, like you say Bankkauffrau Gehilfe. So this is, and you can make this arbitrarily long. English doesn't have the same. And in Finnish, Finnish has even richer morphology than German, so the words are even longer. So this really makes intuitive sense. And we can plot this with even more languages, and we find varying patterns, right? And that we could do all of this using this conditional frequency distribution to compare events across different categories to get some really cool insights into linguistic corpora and their differences. Okay, now we do a second application, namely a Bigram model. And what's a Bigram model? In natural language processing, is a Bigram model is something that gives you well, it could be a probability or it could be a frequency. Let's do it in probability. It gives you the probability that one word is following another word. And in a trigram model is gives the probability that a word is following two other words. And the n-gram probability n-gram model gives the probability that a word is following given n-1 other words. Okay? So let's see how we can make such a so why do we have such a model? First of all, that's useful because we can generate text, as I will just show you in a second. And secondly, the motivation to have this is to generate text. And now the second question is, how do we implement it in NLTK? Well, we can implement it using this frequency distribution, or this conditional frequency distribution that we've just seen, this conditional frequency table that we've just seen. Okay, but let's start by way of illustration. Let's say we have this sentence: in the beginning God created the heaven and the earth. Okay, so this is our text. Then we go to NLTK, we say, okay, let's get all the bigrams from this sentence. We get a bigram object. Then we say, okay, let's convert that into a list. So we get a list of all bigrams. And here's how it looks like. So this is bigrams. So these are two consecutive words. In the beginning God created. So this is a list which consists of pairs of two consecutive words. And now that somehow looks like the pair list that we generated previously. Okay. So what we do is we continue. We take each word as condition. So the first word is then the condition for the following word. And to illustrate this, we take the Genesis corpus from NLTK. We get the words from that for the English Genesis. We make the bigrams, so we make those pairs and feed that into the conditional frequency dist. And now your task is now let's generate text with this CFD. How do we generate text with this? We would first write a function that's for each given word. So you give it a word, and it would find the most probable next word using this conditional frequency dist. And then we start generating, and we implement a function generate model that starts out with some words such as living, and then generates, so it always samples the most likely next word, until we run out of memory, or we run out of time, or we lose interest or something. And now this is your task to do that. So you could stop the video here and try to implement those two functions. And once you've finished, you can continue and check whether it matches the actual solution. So please hold on the video now, and then we continue. Good. So here's the generate model. It finds the most probable next word given some initial word. So, and actually it's doing a little bit more. It's doing this also a number of times. So it starts out with how often are we going to do this? So we're going to do this 15 times. So we make a for loop and going to do this 15 times. We write out the current word. So here in the beginning, it's just the initial word. And we say, okay, no new line. And then we go to our frequency dist. We get the word. We go to the word. And what we get is, let's look back what we get. So we get something like this here, right? So we get a distribution over all the next words given our condition, right? This is our condition, this is the current word, so we get the distribution over all the next words. And the most probable next, so our goal is to find the most probable next word, so it's just going to be the word that has the highest frequency here. Okay, so we're going to pick this word that has the highest frequency. And then we go next in the iteration, we print this word and then following this word, we again get the most probable word given the current word. Okay? And now we would start out with the word living. So we take our conditional frequency distribution, we feed in living. It finds that after living, the most probable word that follows living is creature. So we get living creature. Then we have creature, we check what's the most probable word following creature, then it's going to be that, then he, living creature that he said, comma, and the land of the land of the land. So you see also something here which is very typical for the approach that we're doing, because it runs in an endless loop, right? So you see here this part would repeat forever, the land of the land of the land. Because we get land here and we know what's the most probable next that's going to be off. And once we know what's following off, we know that it's going to be there. So we're going to repeat after land, after, and then we're going to repeat land again. So if you implement it like this, you would generate text that is repeating forever. So in practice, if you want to make that smarter, you would actually sample. Instead of taking the max here, you would actually sample. So let's go back here. You would sample from this. Let's say the word comma has a probability. So you check this. This occurs 3,900 times. You sum up all those numbers and you divide by those numbers. So you will get a probability for the word comma. That would be 90%. And this, or let's say that would be 40%. That would also be 40%, or 30%, 30%, 10%, etc., etc. Now you would pick each word with that probability. With probability 30%, you would pick a comma, but with probability 70%, you would pick one of the other words. And this way, you would not run in this endless loop here that we've seen, right? Okay, cool. Cool. And if you want to check this out on the internet, apparently there's also this autocomplete song. So your smartphone is doing something like that. It has a built-in Bigram model or Ngram language model. So it's also called language model. And with this, you can generate text condition on the previous words that you've generated. And that may lead to some funny situations and to some funny automatically generated text. Okay, cool. So we have seen conditional frequency dist as a NLTK object and as a NLTK functionality that's allowing us to do text generation, and it's also allowing us to do an analysis and a comparison of different of text in Corpora along different dimensions. So I think these are cool cool applications. You can see the functionality here and what it's doing. We can also plot something. And if if you want to check this out, check it out at home. check it out in the practice class and check it out in the homeworks, and maybe check it out in the shared task that we're going to do later on. To finish up with this lecture, we will do some studying and some linguistic analysis of the Brown corpus. So we do a conditional frequency dist, and we have those different genres. Before we had just news and romance. Now we're comparing more genres. And we want to check how do the modals, like the modal verbs in English are like can, could, may, might, must, will. How do they differ across those genres? Now you can imagine, you can think yourself what your intuition is. We tabulate that again without doing the cumulative plot, but just doing a tabulation. How often does can, could, may, might, must, will occur in those different genres? Okay, so you can try this out and be surprised or not what's coming out. Another cool application is, is there anything interesting? Maybe, okay, so like in newspaper, we have the word will occurring more often than in other corpora, whereas in Romance, we have the word could that is occurring the most. Again, so there's one caveat when you compare those numbers. You also need to take into account how large these corpora actually are. So you see the numbers for humor are all very small here, but this could really just be the case because humor has much less frequency. So what would be more interesting to actually check is either you normalize those numbers, so you divide by the total occurrence, the size of the corpus, let's say, or you just look where's the maximum. So in news, we have the maximum at will. In religion, we have the maximum at can. So, and will is not so often, but so it's actually close by, but so can is more frequent. In Romance, we have the maximum at could, and the same happens to be true for humor. Okay, so I'm not sure if that is intuitive or not, but it's certainly interesting. Now let's make an even cooler application scenario. Namely, let's check language change or usage change of words over time. So we go to a temporal to a historical corpus, let's say, namely the corpus of inaugural speeches in NLTK, like presidential inaugural speeches, as we've seen before. Again, we import the corpus from NLTK corpus. We check how do the files look there. They look like, first they give the year, then they give the president name, the last name of the president. And of course, every 4 years we have an election. So they start from 1789, the first US president, then they go to 1793, etc., until 2020, right, more or less. Of course, again, NLTK will not go until 2020. And how do we get the years? We get the years by taking the first 4 characters, right? That's how we get the years. Now, what we're interested in, how the usage of the word America and citizen has changed over the presidential speeches, right? From 1789 to the present, more or less. So we feed in our pairs of a target. So target is the words and the years. So that's where we get the years from. So we feed in this list of pairs into our conditional frequency distribution and check what we're doing again here. So actually we should first start out, if we follow our previous logic, we should first go over the target. So that this is the condition, right? We say we want to have American citizen. Then we get the year. How do we get the year? By iterating over all the files in the file IDs. Then we go over all the words in a specific file ID. And we check here. So what this functionality is doing is if the word lowercase, so we lowercase the word so that so that we also get so that we are case insensitive, right? And we only check whether the word starts with the target. So if the word is American, Americans, Americas, or citizen, citizens, or citizenship, we do not really care in this application. So we only want to check whether the word starts with our two conditions. And then we make all those tuples, right, where we have a word that starts with America or Americans and the years of the file, right? And then we want to check how does the distribution of the word usages change over the years that we have here, right? So we use the CFD plot to plot this. And this is what's coming out here. You see the two conditions, one is America, the other one is citizens. Here you see the years starting from 1789 to 2009. And now you see the usage frequency of those two words. So that, I think, is very interesting for either a historian or a historical linguist, for example, because he could probably detect some interesting patterns. So what we see here now is it seems that the word usage of America has increased over time. So maybe the national identity has become more important over time in the presidential inaugural speeches. What we also see here, there's a peak for the word citizen in 1841, which I lack the historic knowledge to account it for. Maybe it was just the idiosyncrasy of one president. But other than that, we see the word a citizen either has been stagnating or well, we could also say maybe it has decreased a little bit in importance, while the importance of America certainly has increased over time. So this is a really cool application and concludes this lecture. So what we've seen in this lecture is text corpora. What is the definition of a text corpus? It consists of multiple individual text files and individual texts, and it's usually balanced to some degree, has been created either as a crowdsourcing community, such as in the case of the web, or with some purpose in mind, such as like some literature people wanting to create a corpora of poetry, for example. It is characterized oftentimes by different classes, different categories, such as domain, genre, time, and language. We've seen an annotated corpus, where we have said the definition of an annotated corpus is that the individual texts in the corpus are classified along some category. We've also seen how to compare corpora or how to compare distributions within one corpus along different categories. We've also seen how to use Python and NLTK to process text corpora, how to import module, how to use the NLTK functionality, especially the conditional frequency distribution, to do corpus analysis and to do further things like text generation. As we've said, it is not only useful for corpus linguistics to design, create, and analyze text corpora, to describe how language is used and how to compare different languages or one language across different categories. But we can also use that for dictionary construction. For example, find in a historical corpus, find words that have been newly generated, newly coined in the language community, to find out words which are no longer used in a community. We can use the functionality that we've seen to learn text generation models as typing aids, as used in smartphones. We learn the probability of the model suggests to generate the next word, and we can even go more general and generate natural language generation systems that allow us to generate artificial text generated by the computer and to develop dialogue systems that communicate with humans. And this is a currently very, very active and interesting field in artificial intelligence. So here we have seen some of the basics to do that. Here are further links that you may consult for further reading, and what you can do to prepare for the next week is to go over this lecture, recapitulate the basic concepts and the definitions that we've given. Also, you can check the example solutions of the practice class and prepare for the next practice class, and you can go on reading the chapters 2.4 and 2.5 from the NLTK book. And with this, I thank you very much and look forward to the lecture next week.